Hello guys, let's talk about the next subject, stress component by equilibrium. And then here we have little questions. A student ask if we have any lecture in 11:50 in Zoom. But I guess the lecture will be made by my TA. Please discuss with my TA for his class. So we have a TA class after my theory class. Okay. So let's talk about next subject. The next subject is stress component by equilibrium. Alright, so let's imagine one-dimensional member. So we already discussed one-dimensional member the last time when we discussed the tensile stress part, isn't it, right? So here, for example, so if to refresh your memory, so I'd like to draw a member. So let's consider one-dimensional member, and this one-dimensional member is subjected to forces. Then if you consider only a part of this member, because this member is in complete equilibrium, so if you consider an imaginary cross-section, to consider the left-hand part of the member as a free body diagram, then we have force here, the external force, which is the concentrated in this example. And then if you consider force equilibrium, so we can conclude that there must be exact normal stress, which is equal to the force divided by the cross-section area. So force equilibrium says that the force is equal to the normal stress times the cross-section area, isn't it, right? That's what we discussed last time. So here that description is given in the first diagram. So let's consider the second one here. So instead of talking about a normal cross-section, I want to consider inclined cross-section. So as we discussed next time, if you consider any inclined cross-section, then usually we need to consider, the normal stress component and the shear stress component. Why we have such kind of normal stress component and shear stress component? How we determine the normal and the shear stress components. Okay, that is the subject in this section. Okay, that discussion is so simple. All right, so let's go back to this example again. Then I want to move it back. Okay, so instead of talking about a normal cross-section, I want to consider an inclined cross-section here. An inclined cross-section like this. Okay, inclined cross-section. So if we consider inclined cross-section, then I have another free body diagram which is different from the last time. Okay. Alright, so I have force. So if you consider the area here, so if you consider this area, let's say A inclined, okay, A inclined, then again by the force equilibrium, if there is any stress component in this direction, sigma, the sigma times the inclined cross-section should be equal to force F, okay? And then we can determine the magnitude of normal stress by dividing the force. Normal stress is equal to force divided the inclined area, okay? That is force equilibrium. There's no problem. But what's the reason that we have to consider so-called normal stress and then shear stress? That is the question. The reason is, look at this. So when we discuss in the first example, there's a point that we didn't discuss, we didn't mention. What is it? So we already consider implicitly a coordinate system here. Because this is a one-dimensional coordinate system, the coordinate system that we want to we already consider implicitly is what? So we want to consider a coordinate system x and y here. Okay? So if you consider a certain coordinate system, because we consider a certain coordinate system, there must be a normal in this direction, normal vector. And then also, if you consider a normal cross section here, so I must have normal component, isn't it? If anything, perpendicular to the normal direction, so we want to consider tangential direction, and then the tangential stress component is called shear stress component. So everything comes from the definition or the introduction of a coordinate system to our analysis. For this inclined cross section, so if you have any arbitrary cross section, this is normal, isn't it, right? This is another normal here. Then because we have this normal, then we can introduce another coordinate system like this. X prime. So prime means this is different from the original one. And then as long as we are using the right hand rule, then we have y direction. Okay? Then similar to this, because we similar to the last example, so we want to consider any stress component in the direction of new coordinate system. That's what we want to do. Because from the middle school and high school mathematics, so we have discussed the way of dealing with vector components for many years, isn't it? So we are very familiar with that discussion. That's why we want to use the knowledge regarding the coordinate system. Okay, that was the reason. So here what we want to do is we need to decompose this vector into two different components, normal direction and the tangential direction. So if you divide this normal force component by this area, then we can obtain the normal stress magnitude and then shear stress magnitude. So everything comes from the equilibrium consideration. And then here the key point that you have to understand is the reason that we need to consider the normal stress and the shear stress instead of this inclined stress component is what? Actually this is exactly the same as before, that definition is satisfy the force equilibrium condition, no difference. But what we want to consider is what? A coordinate system, a certain choice of coordinate system. So if we want to use this that choice of coordinate system, so I need to decompose the force into two different force components, so following the direction of coordinate system. And then if you divide the force component by this area, then we can obtain normal stress and shear stress very, very easily. Do you have any question for this discussion? Please feel free, if you have any discussion, please use the chatting window. You can ask any kind of questions. Except my age. Okay, so now let's consider more arbitrary cases. Okay, so here we want to consider the same geometry, but instead of force in parallel to the x direction, we have very arbitrary directions of the forces. Okay, so here as I told you before we discuss anything, so we want to define a coordinate system x and y here, since we are in two-dimensional space. So if you cut this cross section, and that because the force distribution is completely arbitrary, and then the distribution of traction is also arbitrary. The directions, various directions, and then also the magnitude, the distribution of magnitude is also non-linear. It's not uniform at all. Okay. So as I told you here, for the global analysis, we want to introduce a coordinate system x and y here. And then if we want to discuss any stress component with respect to this inclined cross section, so I want to introduce a coordinate system, new coordinate system, x prime and then y prime. Okay, so in these two directions, so we can consider these two normals, normal vectors and then shear vectors. Okay, tangential vectors, because they are orthogonal to each other. The dot product of these two vectors should be equal to 0 by the definition. And then let's consider a decomposition of the traction. So we have, as we discussed in the last note, we have an arbitrary distribution of traction on this cross section. So again, since we have, an orthogonal sets of coordinate directions, so we can decompose this traction into the normal component and the shear component here. So the normal component, its direction is given by the normal vector here, normal vector, and then its magnitude. So as you see here, the magnitude depends on the position, isn't it, right? Here we have minimum normal stress component, and we have maximum normal stress components. It depends. Here x bar means we are talking about a vector, a combination of x and y positions. Okay, and again for the distribution of shear stress too, so we want to use this the tangential vector to represent direction. Make sure that this normal is equal to 1, and then the magnitude of shear stress depends on the position. Is it clear? So according to the force equilibrium, superposition of these two distribution of traction should be equal to the original distribution of the traction. Okay, so here again the distribution of normal stress is non-linear. It is not easy to deal with. So we'd like to introduce a further simplification. Okay, in these undergraduate courses. So we are not ready to deal with this non-linear distribution of normal stress and shear stress tractions over the cross section. So instead of dealing with this, the real actual distribution of normal stress and shear stress distribution, so we want to consider the average one. Okay, the average one. So upper bar means average. Okay, the upper bar means average. So this actual distribution, finally, this actual distribution of traction is simplified by means of combination of the average normal stress and the average shear stress. Okay, that's why in our textbook, so we always use the average normal stress by using just overall, we with an assumption that the normal stress distribution is constant over the cross section. But in actual problems, if you solve these problems using the finite element method, or for example, if this is very advanced, numerical packages to solve the mechanical problems, you can easily find out that this distribution of normal or shear stress over a certain cross section is not constant at all. In most cases, is non-linear. Okay, so here. The average normal stress and average shear stress is just simplification. As long as it satisfies the force equilibrium, so we'd like to use this simplification. Okay, now let's discuss how we calculate stress component by using the force equilibrium. So we have different forces. The rule underlining our discussion is sum of all the force factors should be equal to 0, because this is a force equilibrium. So the calculation of the force factors is not that convenient as is, isn't it? So instead of dealing with the vectors directly, we want to introduce a coordinate system, x and y. So if you do that, then instead of dealing with vectors directly, so we can consider the force component only. Okay, the force component only. So for any sum of force component in the x direction should be equal to 0. And the sum of force components in y directions is equal to 0. Okay, or instead of using this x and y, So we can follow, this new coordinate system, x prime and y prime, okay? The same thing. So the change of coordinate system doesn't change the nature of force equilibrium, okay? It doesn't change the nature of vectors, but the numbers that we have to consider in the direction of the coordinate system would change because the direction of coordinate changes. So even if you consider the same vector, for example, let's consider this vector here. So I have a vector. Okay, I have a vector. Then first, let's consider this black coordinate system. Let's consider black coordinate system x and y. So if you do that, then the projection, the x component is what? The x component is here. This is x component because this is projection. The y component is here. Okay? Isn't it? This is for the black coordinate system. So let's consider blue coordinate system. Blue coordinate system, let's consider an extreme case that a blue coordinate system x prime and then y prime. So in this case, the projection of this vector to x prime, the blue x is what? This is projection. But how about in the y direction? The y direction is nothing, isn't it, right? Nothing. So although we deal with the same vector, but the numeric values of the x and y components depends on the choice of coordinate system. This is very important, okay? So here I'd like to finish my lecture on the stress component by equilibrium. So let me take about 10 minutes break, okay? This is 11:07, and then we'll resume the next lecture at 11 around 17. So I will announce in advance, okay?